Hey guys, we're going to start talking about limits, and we'll just start with an informal definition of a limit. So as f of x becomes arbitrarily close to a single number, we'll call that L, as it approaches C from either side, then the limit of f of x as x approaches C is the value L. This is written as, here's our limit notation, limit as x approaches C of f of x equals L. As we're going through work in this chapter with limits, you have to write this limit notation every single time. It gets tedious, but it is worth points on the AP test. So here's kind of what we're talking about. Here's some function f of x. Here's a y value L. We've got x approaching from the right. It's kind of far away from C right now, so it's got a higher value. The closer it gets to whatever that value L is, f of C equals L, closer and closer. And the same thing can be approached on the left side. So x is now to the left of C. It's getting closer and closer to that point. And the more we zero in on it, the more x approaches C from either side, it hits that value L. So we're saying that that limit is L. It's not going to be any higher than that value. It will not be any lower than that value at C. The actual value f of C doesn't matter. So whether or not C exists, so the limit as x approaches 6 of f of x, even though in this picture, even though f of 6 does not exist, the value it's approaching is 4. So that limit is equal to 4. It's approaching 4 on the right side and on the left side. Even though in the middle picture, f of 6 equals 5, but the actual value of the curve on the left and the right, you're zeroing in on that value of 4. So that limit is also 4. And finally, the limit as x approaches 6 of f of x. Oh, this one's already filled in. That equals 4, even if f of 6 actually equals 4. So here, f of 6 did not exist. Here, f of 6 was equal to something else, like 5. And here, f of 6 was actually equal to 4, and that happened to also be the limit. Sometimes we're interested just in one-sided limits, and so this is more about the notation than anything else. If f of x becomes very close to L as x approaches C from the right side of C, then all we do is add this little plus. It's kind of like a superscript or like almost in an exponent position. The limit as x approaches C from the right of f of x equals L. If we're approaching, if x is approaching C from the left side, then we use similar notation, the limit as x approaches C with this little negative sign right here of f of x, that would also equal L. This is important, and this pops up, or you use this idea in a lot of multiple choice questions. In order for a limit to exist, so for a limit to actually exist, the limit from the left and right must be the same. And this is an argument we're going to use all the time for what a limit value is or whether or not a limit exists. So like in this example here, the limit as x approaches C from the right of f of x. So now you're on this side of C, you're on the right side of C. What are we approaching here? Let's assume these are unit values, so 1, 2, 3. That limit is 3. The limit as x approaches C from the left, so you're coming up here and get close to C, that limit is 1. Since those two limits do not match, then there is no limit as x approaches C. You can't say we're honing in on one single value. So equals no solution or does not exist. Either way for that one. Sketch the graph of f of x equals x squared plus 2x minus 3. So now we've got to try to remember how to, we've got to try to remember how to graph these things. Remember, you start by factoring. X plus 3, x minus 1. Think back to your rational function days. This one turns out to be nice and easy. It simplifies to f of x equals x plus 3 because these x minus 1s cancel. And remember, this is basically just a line with a hole. The hole is at 1. X can't equal 1. But you still have to plot it in line with the graph. So if you plug 1 into the simplified function to figure out where to plot the hole, 1 plus 3 is 4. So there is a hole at 1, 4. Let's put that right here. Otherwise, it's a line. It's got a y-intercept of 3. It's got a slope of 1. So sketch that graph like that. So if I were looking at this problem, I might say something like, let's figure out what's the limit as x approaches, how about we hone in on that hole, x approaches 1 of f of x. Pay attention to your notation. If this was g of x, I'd write g of x right here. What is that limit equal to? Well, the value that we're approaching here, you're coming in on 4. So that limit's equal to 4. You can check things numerically. This gets pretty tedious. Some of our bookwork has you filling in little tables like, all right, if we are looking at a limit as x approaches 1 of some function, we're approaching 1 and trying to figure out what is that limit. If you're kind of far away from the left, you're at 0.75, you get this value. If you get a little closer to 1, but not quite 1, you get 3.99. If you get a little closer to 1, you can see 3.999. You can keep going until you're satisfied that, oh, this is going to be approaching 4. Same thing on the other side. You're kind of far off from 4. The closer you get to 1 from the right side, the closer you get to the value of 4.0 perfectly. So again, you would just keep adding decimals until you're satisfied. But we're looking at numerically what is the limit at 1. It appears that the limit is 4. What is f of 1? Remember, it came from this rational function. What is f of 1? F of 1 does not exist. The value of the function at 1 is not defined. It's a hole in the graph. When you're working with this numerical approach, be careful if you're oscillating. So let's see. I have my graphing calculator open. Turn off a couple things here. So that was, we were looking at sine of, what was it? Pi over x. Let's see. I'm going to switch my mode. In calc, you should be in radian mode all the time. So if you're in degree from physics, make sure you're switching back and forth. Gosh, I don't know. I'm just going to zoom 6 on this. Check out what's happening in the middle here. The limit as x approaches 0 of sine of pi over x. This limit does not exist. I can zoom in on that. Let me show you another feature. Zoom box is kind of nice. It allows you to draw a box. So this is harder on my computer than it is for you with a handheld device, but get your cursor up to a corner of a box you'd like to draw, press enter, and then drop that box down, drag it over a little bit. This is basically saying, please make my window this, and then you press enter, and it says, okay. What is the limit as x approaches 0? I don't know. Crazy things are happening, and if we keep zooming in, it's going to keep oscillating. So there is no limit at 0. Now, is there a limit? Get back out here. If I say, what's the limit as x approaches 3, we're not oscillating anymore. There is a limit right there, whatever that y value is, but not at 0 where the oscillation happens. Oh gosh, sorry, I just jumped all over. Okay. There we go. So that limit does not exist if it oscillates, and that's going to happen with trig functions with like crazy. Think back to graphing. If I said, what's the period of this thing? It's like, what? Because that's not x is to a -1 power. What are other limits that fail to exist? So we already talked about this. If the left side is not equal to the right side, so the graph has some sort of a break and a jump in it, if the function oscillates between two values as we approach c. Then the third scenario is if the function is unbounded. What does unbounded mean? Think vertical asymptote, like a rational graph. If I say, what is the value of this function as it approaches whatever the c value is, that's infinity. There is no limit. Infinity is not a number. So there is no limit to the function at that point. You can see that numerically here. I know it says complete the table. Hopefully your shell notes have the table already completed, but let's check out this rational function. The limit as x approaches 3, which we should know is the vertical asymptote because it's the undefined value in the denominator. Can't be simplified away. What is the limit at 3? Or as x approaches 3. You can try this numerically. Come at 3 from the right side. 4, 3.1, 3.01, etc. The numbers just get bigger and bigger and bigger. Come at 3 from the left side. A little bit under 3, like 2, get closer to 3. These numbers just grow like crazy. If you keep adding decimal points on either end here, decimal places, I should say, you're just going to get larger and larger numbers. So that's showing you, hey, on both sides, these numbers are growing to huge positive values. That means that we have a limit that does not exist. The function is approaching infinity. So what is the limit as x approaches 3 of x squared over x minus 3 squared? We can write no solution. We can write does not exist. You might see the DNE thing on my homework. On the AP test, these are mostly going to be multiple choice type questions, so they will probably write out the phrase does not exist. All right, and so now you're going to want to work on, pause my video, and you're going to want to work on this little practice sheet, and then when you finish, unpause, and you can check my answers. I am going to be explaining through it, so you might have to jump ahead a little bit. Assume all of these tick marks are 1 unit. All right, so if you missed any of these or you're not sure what to do for some of them, we're just going to go through. Pay attention to notation. The limit as x approaches 5 is here. So we're looking at this point. That limit is equal to 3. It's coming at 3 on both sides. I'm going to go down. The limit as x approaches 2. What are we zeroing in on? Right here. 1, 2, 3. The limit as x approaches 4. 1, 2, 3, 4 is the vertical asymptote. There is no limit to the problem, so it does not exist. The limit as x approaches -5 from the right. So 1, 2, 3, 4. Here's -5, but you're approaching from the right side. So what is that limit? That limit is equal to 1. The limit as x approaches -5 from the left side. Here's -5. Approach it from the left. You're zeroing in on the y value, 0. The limit as x approaches -5 in general. Well, the right side and the left side do not have the same limits, so this limit does not exist. F of 2, remember that's not limit notation, that's just saying what is f of 2? It is this point up here, which is 1, 2, 3, 4. Does the limit as x approaches 2 of f of x equal f of 2? We answered this limit back here. We found it to be 3, or look at your graph. Does this limit, does where the graph continues from one side to the other, does that limit match that point? No. Does the limit as x approaches 5 of f of x equal f of 5? 1, 2, 3, 4, 5. That's this guy right here. This point is defined. F of 5 is equal to 3, and the limit is also 3. So, yes. Find the limit numerically. You can do this all kinds of different ways you would do this on your calculator, first of all. You can do it a lot of different ways. You can just type things in, but you should be in radian mode for this. Let's see. I kind of like the idea. I also want to just show you some things on your calculator. So it was sine x divided by x. And my window was pretty zoomed in on the middle there. So if you don't know about this yet, we want the limit as x is approaching 0. Now, Okay, if I have my graphing calculator, actually, to save time, I'm not filling out this table. We would never use a numerical approach if we're allowed to use a graphing calculator. So I'm saying, if you need more investigation, check out my key that's filled out. But it says draw the graph, use the trace feature to confirm your numerical conjecture. Well, if I've got a graphing calculator and I'm plugging this in, I'm not bothering with numerical, and they wouldn't ask you such a thing on the AP test. Anyway, use the value feature to confirm. Okay, so what's this value feature we're talking about? What's this trace stuff? You should know about trace. If you trace, you can see like, as I'm approaching 0 from the right side, it sure looks like I'm hitting 1. But then see where it says 0, y equals nothing. And then from the left, yep, the closer we get to the left, the closer it's getting to 1. If I try to use the value feature, that's in the second trace, which is the calc menu. You're going to be here all the time. You should have been here all the time in pre-calc and also maybe in math 3. So value, as long as you can, I believe you have to be able to see it in your window, but as long as the x value is in your window, you can say, hey, tell me what the function is at x equals 0. And the fact that it's coming up with this nothingness means that's undefined. If you want to try that for another value, let's just put in 1. When x is 1, you do get a value for y. So this is the method I was about to use to fill out this table, and then I realized, well, that's dumb. If I'm looking at a graph, I'm not going to fill out the table. All right, so what is that limit? That limit is 1. But what is f? Let's assume that's f of x. What is f of 0? Undefined. Because sine of 0, we should know is 0. But 0 divided by 0 is not actually equal to 1. 0 divided by 0 is a whole other thing that we get to talk about in the future. It is called indeterminate. And ignore this. It's a factoring problem copied from something else. All right, that's it for today. You've got some book work, I believe, for homework tonight. Please email me or visit office hours if you have any questions.